Hey guys, I hope you can see the white screen. Um, Today I'll not be like covering everything under the course content. Basically, I'll be covering some of the things that I'm mostly familiar with and also could refer from my notes. So first I'll just go through some of the basic core concepts and then we'll gradually move on to the advanced stuff. Um, so yeah, let's start. Okay, let's start from the very beginning. So the what happens when you actually press the power button on your machine. So this is called the OS boot up process. So we'll be looking at some of the things that are happening inside after you press the power button. So the first thing which executes is the BIOS. So this is a ROM which has like some instructions to actually start the machine. So the BIOS has something called post, which is which is called power on self test. This is a process which is immediately performed after the machine is turned on. This is part of the device's pre-boot sequence. So what this post does is first it looks for the MBR. So a lot of new words here. MBR, which means master boot record. So what's this MBR? This is actually something that resides in our hard disk. So this is like a visual representation of that. Basically, MBR is also called the sector 0 of the hard disk. It first has a magic number and then the partition table and then the boot code. So what is this magic number? The magic number is actually something that is used to indicate that this is the MBR so that the BIOS can identify that. And then we have the partition table. So this is the way the hard disk is partitioned. And then the boot code, which contains the instructions to load these other parts of the hard disk as well as loading the rest of the OS into the memory. So this is called the MBR. So what this post does is first it looks for the MBR and if everything is right, then it moves on. Next, I'll I'll just give like 5 seconds before clearing this white screen if you want to take any screenshots. Okay, and then we can move on to the interrupt descriptor table register. This is called IDTR. This is actually a special register within the x86 architecture. Basically, this is also called the interrupt vector. First, what's an interrupt? An interrupt is actually anything, like it can be a timer interrupt as well, or it can be something external like the click of a mouse or like pressing of a key or the like touch screen, anything external. So when this happens, when interrupt happens, the OS or the BIOS uh, needs to actually stop what it's doing and then handle that interrupt. So this interrupt vector is a register which is set by the MBR, and it is actually kind of a pointer which points to some part in the memory where the interrupt service routine is located. So this is actually a kind of a value of an address. This when an interrupt happens, the value in interrupt vector must be copied to the program counter, which is known as PC. So you know what PC is. This is also a register which contains the value of the address of the instruction, which should be executed next. Yeah. So these are really important concepts, this interrupt vector and program counter and the interrupt service routine. Uh, so yeah, the next thing would be context switching. Again, this is also related to the interrupt vector. So basically, an OS, if you consider an OS, it doesn't exactly run a process and run only one process at once. It actually like runs simultaneous processes at once. So then sometimes there may be some instances where you need to save the state of one process and then uh, change the process that is executing on the CPU. So assume that you have P1, which is currently executing on the CPU, and sometimes you may need to save the state of P1 and then execute P2 on the CPU. So since we have limited resources, such as the CPU, we need to the OS needs to do this kind of things. So the context switching theoretically means that saving the or storing the state of a process so that it can be restored and resumed at a later point. So this is part of the multitasking feature of an operating system. Okay, so then to understand, to save the state of a process, we have something called process control block, PCB. The process control block has some characteristics which are associated with a process. So it has a state and it has a number and program counter, register values, memory limits, etc. There might be some other things. So basically the state of a process means that wait, I think I have that diagram. Yeah. So a process can have like different states, ready or running or suspended or something like that. So the process control block also has the state of a process, and then it has a unique number. So this number is kind of like an identifier, and then it has the PC program counter value, so the address of the next instruction of that process, and then the register values, whatever the registers it currently uses, and the values that are contained within it, memory limits, etc. So these are like some of the things which are used to identify a process. So PCB is actually used to represent a process within the memory. So yeah, I think we have some of the basic things cleared up. So let's go over to the OS boot up process. So this is kind of like a flow chart. It's easier if you can get the bigger picture like this. So the very first thing that is executed when you press the power button is the BIOS. Execute BIOS instructions. And then we move on to host. After this, host looks for the MBR and it loads the MBR from the disk to the RAM. And after that, we pass the control to the MBR. So jump to the starting point of MBR. So whatever the very first instruction in the MBR, we jump to that point. That means like we are changing the program counter value to the address of the first instruction in the MBR. Now the MBR contains instructions, as I mentioned before, to run the boot code, right? So the next step would be to run the boot code. Then we have to handle, at this point, we have to handle whatever, if there are any interrupts, then we have to handle those interrupts. Then we have to set up the interrupt vector and interrupt handler. Okay, this means like updating the value in the interrupt vector to the address of the interrupt service routine. The next step would be, now that we have the register value set up, we can actually look for any interrupts. So we are constantly looking for interrupts here. Now suppose if there are no interrupts, then we can proceed to loading the other parts of the hard disk and the OS. So the next step would be copy the other parts, let's say sectors, to the RAM. And then there's something called ring levels. Change ring level to 3. So all the processes, like I'll pronounce this word as processes and this word as processors just to avoid the confusion. So all the processes executing in an operating system can have like priorities. These priorities are represented by these ring levels. So ring level 0 means the highest priority and 3 means like the lowest priority. So at this point, since the OS and everything is loaded into the RAM, we are changing the priority level to the lowest priority so that the user can execute any user level programs in this ring level. So we are updating the ring level to 3, and then we have to initialize a timer interrupt. This timer interrupt is actually set because we are trying to ensure that not even the OS can occupy the CPU constantly without any interrupt. So we are not going to give the control of the CPU 100% to any process, even if it's the OS. So even the OS actually runs according to an interrupt. We can't see it, but it's like a very minute level of timer interrupt that we set so that there's an interrupt service routing running in the middle of that. So we set the timer interrupt, and then we run init, which is like the very basic user level process. And then we can, yeah. Okay. Now, suppose there's an interrupt. At this point, we have already set up the interrupt vector and interrupt handler. So if there's an interrupt, we can actually execute our interrupt service routine. So for that, what we do is we copy the interrupt vector value to PC, which is the program counter, and then we execute the interrupt handler or the interrupt service routine. Okay. Yeah, it's kind of a bit messy, but don't mind that. So this is basically what is happening at the OS boot up process. So first it's BIOS, then POS, then loading the MBR, then running the boot code, then setting up the interrupt vectors, interrupt handlers, and then if there are no interrupts, all of this happens while constantly checking for interrupts. Then we change the ring level to 3, initialize a timer interrupt, and then if there's an interrupt happening, then we can just copy the interrupt vector value to PC and then execute whatever that, however we are going to handle that interrupt. So this, as I remember, this was actually the very initial part of the course content. I think there were like much more in detail stuff there, but this is like the overall process. Is there any question from this part, or shall I move on forward? I'll give you like 5 seconds. Okay, I hope everything was clear. The other thing is, before moving on to like inter-process communication, there's something called threads. So there are programs and there are processes and there are threads. So a basic unit of execution is called a thread. So a process can have actually many threads. For example, this is just an example. Yeah, suppose like consider this Chrome. So take Google Chrome as a process, then you can see that there are like several other subtasks running. So these are kind of like threads. So a thread can actually look after one specific task. So one of these can handle what if there's a song playing, then it can handle that part, or something else can handle if there's something downloading, then another thread can handle the downloading part, etc. So something like that. So this threading, or the processes can actually be divided into two categories: single threaded process or multi-threaded process. So the advantage with multi-threaded processes that it can perform like multiple tasks or multitasking. So it's kind of advantageous. So then let's move on to the one of the major topics, which is inter-process communication. Process communication. So we have discussed that an OS doesn't actually run a single process at once. It actually handles multiple processes. So these processes can be divided into two categories. They are independent processes and cooperating processes. So a process can be divided into two, which are independent, and then we have cooperating. So independent processes, as the name suggests, they are independent. So technically it means that they cannot affect or be affected by other processes in the system. Whereas cooperating processes can affect or be affected by other processes in the system. So if any process shares data with another process, automatically it falls under this cooperating processes. So there are like advantages or like necessities why a process needs to communicate with another process. So you can look more into that. So basically we will be considering cooperating processes here. So when we consider cooperating processes, there are basically two ways that two processes can communicate. The first method is shared memory, and the second one is message passing. So this message passing was actually not there in the course content when we were learning it. It was more of a self-learning on my part. So I encourage you to look more into that. So the thing that we are focusing here is the shared memory part. So shared memory, when we consider shared memory, basically it's a very simple concept. There's a part of memory which is shared among the cooperating processes. So let's imagine this is that, and suppose there are two processes, P1 and P2. So if P1 needs to communicate with P2, what it can do is it can simply write data into here. Let's say I equals 2. So if P2 needs to communicate with P1, similarly, it can write into here, or else when P2 needs to get the value of I, it can simply look at this shared memory and it can see, I is equals to 2. So technically, this means that processes can exchange information by reading or writing data to the shared region. So you can see that this actually is this shared variables. For example, in our case, I. Shared variables can create synchronization issues. Because as you know, suppose that P1 has instructions like this. So it has several instructions. Suppose these instructions are actually with respect to this I value. So it uses this I value. And similarly, P2 would also have instructions that would access this variable, shared variable I. So let's assume that it's this. Okay. Now we know all this context switching and interrupts and everything that is happening. So suppose an interrupt or a context switch happens in between these instructions. Let's say from here. At this point, let's say a context switch happens. So it already changed it already changed the value of I. However, in the middle of that computation, a context switch happens, and now we are trying to execute this part. And then again, a context switch can happen and it's trying to execute this part. So it's kind of a mess, right? And the value of I will be like, it would give an erroneous value. So this is the problem that we have with interprocess communication shared memory. So when we have a shared memory, it can create concurrence issues. So we have to have a proper method to handle this kind of problem. The problem here is that all of these instructions, they don't they are not executed atomically. So an atomic instruction is something which is executed as a single instruction. So when you consider like one of these instructions, that's an atomic instruction. But since we are like a thread is not an atomic instruction, context switches can happen in the middle. So therefore, there can be synchronization errors. So this problem is called a race condition. You have to remember this word. This is called a race condition. Basically, a race condition is a specific thread which creates a problem. And then there's the critical section, which is the particular segment of the code which creates this error. So in our case, it's the one that I highlighted with this red box. So these are the critical section. This is the critical section with respect to P1, and on the right side we have the critical section with respect to P2. I'll erase this. So when we consider the general structure of a program, we can actually write it in this way. There can be an uncritical section at the beginning. And then it can be followed by a critical section and then again an uncritical section. So our problem is this part. So remember, this is the part where a process will try to change whatever that is in the shared memory area. So what we should do here is we should protect and execute this part atomically so that um, when context switches happen, when a process is executing this critical section, it should not give any erroneous value. So the simplest, most simplest solution would be to disable interrupts within this region, right? So when a process is executing a critical section, we disable interrupts. So the disadvantage of that is that it's actually a dangerous thing because we don't know what kind of a program it may be. It can also be malicious. So now when we consider the general structure of a process, we can actually write it in this way as well. We have the entry section and then the critical section, exit section, remainder section, and then while true. Okay. This while true is actually used to denote that this is a recurring problem. So we have some new stuff here, this entry section and the exit section. Basically, this is the thing that we are going to protect, right? So we are actually introducing a technique that we are using to protect our critical section and to ensure that it is executed atomically, which means like a single instruction. So the most simplest solution using this format would be the turn variable, which was there in the slides. Let me take that. Yeah, okay. So this is the solution with turn variable. So as it suggests, the turn variable is actually used to indicate that it's the turn of some process. So let's consider two processes. Sorry, processes. I'll clear this. Now let's assume this is PI. And what we are going to do here is using the turn variable, we are going to do something for this entry section and exit section. So for the entry section, we can modify that as while turn is equal to J. And for the exit section, we can say turn is equal to J. Okay. And then we can have another process, Pj, and here this turn is equal to I. Okay. So assume we have two processes, Pi and Pj. So initially we have a variable turn. So let's say this is the variable turn, and initially its value is I. So this means that its ith processes turn to execute the critical section. So therefore, initially let's assume turn is equal to I, and then this pi will execute. Now when it comes here, you see that while turn equals j, this condition, is it true or false? So if turn is equal to I, then this condition will be false, and therefore it can enter the critical section. Suppose now that pi is in its critical section, it's going to do some calculations in the shared memory. Suppose there's a context switch happening here. So then from this point, pj will execute, and then it will come here. What will happen at this point? Turn is equal to I, therefore this while loop will run forever. So therefore it cannot go beyond this. It will get stuck here. This is called when a process keeps waiting at this point, it is called busy waiting. So at this point, pj is actually busy waiting, and it cannot go beyond that point. So even if a context switch happens when pi is in the middle of executing its critical section, nothing actually happens, because we have actually blocked pj from entering into the critical section while pi is also there. So after this, let's assume now pi has finished its critical section. So then what it does is it changes the value of turn into j. So now the variable turn will be equal to j. At this point onwards, at any point, if there's a context switch happen, now this pj will not be busy waiting, because this condition while turn equals I will become false, and therefore it can enter its critical section as well. So you see, using a simple turn variable and an enter section and an exit section, we have kind of blocked in any other process from entering into the critical section. So this is a kind of simple process using the turn variable. In the slides, there are some conditions here. So these are the 3 conditions that are like necessary for an ideal solution to a critical section problem. So you have to remember this. The first thing is mutual exclusion, which is what we talked about, that when a process is executing its critical section, then we cannot allow any other process to execute their critical sections as well. The second thing is progress. This means that if a process wants to enter its critical section, then we cannot postpone that process from entering it indefinitely, which means we cannot keep it waiting forever. The third point is bounded waiting, which means kind of similar to the second point, but it says that there must be like a maximum number of times that it is allowed to wait before entering the critical section. So now that we have the criteria defined, we can move on to some other solutions for our critical section problem. So the other thing is, this one, test and set instruction. So this is basically a hardware solution for our problem. Let's go to the whiteboard. I'll clean this. So we have this test and set. Observe this, like you have to remember what is happening with this function. So when you send a value target to this method, it stores that in a Boolean, and then it returns that Boolean. So you see, whatever you send to this target, as the value of this target, it will return that. So if you send true, this will return true. If you send false, this will return false. However, it also changes the value of the target. So at the next point, at the next iteration, if you may, the value of the target will be set to true. So it returns whatever you send initially, but also changes the original value to true. So this is the idea of the test and set hardware solution. So we can use this to address our critical section problem. Let's see how. Let's go back to the slides. Yeah. So this is the solution. So you see, it's the same structure. We have the, let's copy this. Okay. So we have the entry section here, and then the critical section, and the exit section, and then the remainder section. So it's the same kind of structure, but we are trying to modify the entry section and the exit section to improve our solution. So here we are using the test and set and this lock variable. So suppose initially, as before, with the turn variable, we have something called lock, which is a Boolean. So initially this is false, which means metaphorically the critical section is not locked. So that is false. Therefore, when a process initially tries to enter the critical section, when it goes and checks here, test and set, and it sends this lock value, initially it was false and it returns false, but not before changing its value to true. So now the lock is true. However, at this point, it will return false. Then it doesn't get stuck in this infinite loop. It can enter the critical section. Now, suppose while this process is in its critical section, another similar process tries to access its critical section. What would happen? Then same way, this is a same structure is used. So at its entry section, it will check while test and set with the lock variable. And then what would happen is, since lock is true, it will return true. And also it will again set the value to true. There's no difference there. But since it returns true, any other process will get stuck at the first instruction, at the intersection. So you see, through this solution also, we have ensured that only one process can access the critical section at a particular time. And then after executing its critical section, it changes the lock to false. So at this point, if any context switch happens, then it will again check with test and set with the variable lock. And since it is now false, it should be false. Since it is false, the test and set will return false by again setting the lock to true, so that it keeps on happening. So this is the test and set solution. However, so this solution actually has the mutual exclusion and the progress. However, it cannot guarantee bounded waiting. Why is that? Because you see, the next process which can actually enter its critical section, that is actually dependent on the OS or the way the context switches happen. So coincidentally, any process can like wait on forever until it will get a chance to like get scheduled by the process by the OS. to enter into its critical section. So this test and set solution doesn't actually provide bounded weighting, but it provides the other two criteria, which is the mutual exclusion and progress. So then we can improve this. Yeah, this one. So then we can improve our test and set solution to provide bounded weighting. So this seems like a long, complex code, but it's not actually. So we are actually using this weighting array to provide a slot for each process. So suppose there are n processes here. So currently we are looking at the structure of the ith process. So initially this is true. This means this is waiting to be executed or to enter into its critical section, and the key is true, and we have a while loop. Now, mind that while loop doesn't end here. There's no semicolon here. So this is actually a loop. So while waiting I and k. So since both of this is true, at the first iteration, this while loop will return true, and then we can enter into this code segment, which is test and set lock. So initially the lock will be false. Therefore, this key will be false. However, after this, the lock is set to true by the test and set method. So now the waiting I will be false because it's no longer waiting. It can enter its critical section. So since we have locked the critical section, again, at this point, if a context switch happens, another process cannot execute its critical section because we have blocked it. So after this, so all of this belong to the entry section of our general structure of a process. We have modified it even more. And we have the critical section. Now, at the point of exit section, we have all this. Why do we need all this? This is to find the next process to be executed. So we are now trying to ensure bounded waiting here. That means we are not going to put the responsibility to the OS to find what the next process is in order to avoid starvation. So what we are trying to do here is we are trying to find what is the next process that should be executed after this. So let's say j is equal to I plus 1 mod n. So this is like the next value in the array. So using this loop, we are traversing the array and finding what should be the next process. J not equals to I means we are trying to ensure it's not the same process which is currently executing, and not waiting j means we are trying to find a waiting process that is waiting to enter into its critical section. While this condition is true, we are incrementing j one by one and trying to find something. And after exiting, which means that we have somehow either gone through the array or we have found a value for j. If j is equal I, then lock is equal to false. That means it's the same process. Else, we have found another process. So what we do is we don't change the lock value here. We change the waiting value. So that means for all the other processes, the critical section is locked. However, for the j process, if you look at this code within the context of j, then this section will be false. Waiting j is false because this is set by the previously executed process. So then only j can move on forward and enter it into its critical section. So this solution has all three properties: mutual exclusion, progress, and bounded waiting. I hope that was clear. And There are some other solutions similar to this, compare, swap, and Peterson solution. Basically, it's the same thing. You're just modifying the entry section and the exit section with different kinds of variables to ensure that we provide the three categories necessary for the critical section problem. I hope there was no question from this part. Yeah, so next thing we are going to look at is semaphores. Semaphores are kind of like variables which is provided by the OS. Now we have discussed solutions provided by the hardware, and we are going to solutions provided by the OS. So you have to actually remember these definitions. So this wait and signal, or otherwise called P and V, are the operations that we use to access the semaphores. They are basically variables. So wait is used to decrease the value, integer value, whereas signal is used to increase the value. So this while loop is there because we are trying to keep it within the positive range. So we are not going to go to the negative side. Yeah, so yeah. So we have some classical problems here, three problems basically: bounded buffer, readers, writers, and dining philosophers problem. We are going to solve these problems using different semaphores, which means integer variables provided by the OS. So the bounded buffer problem, let's look at that first. It's actually we are trying to consider two kinds of processes, which is a producer process and a consumer process. So initially we have this set of semaphores that we are going to use. N means the number of buffers. So buffers are used to store the resources produced by a producer process. So producer process produces resources, and then a consumer process will consume them. So we have two types, and N is used to denote the number of buffers that is available to hold the resources. And we have these semaphores, mutex. So as the name suggests, this is used to perform mutual exclusion. And we have a full and empty semaphores. So full is used to denote the count of full buffers, and empty is used to denote the count of empty buffers. So initially these are the values here. You have to have an idea, this is how we initialize this setup. So mutex will be 1, which means any process can enter the critical section. Fully 0 means currently we haven't any resource within the buffers, so the full count is 0. Empty is initialized to n because all the buffers are empty initially. So this is the setup. And when you look at the producer process, this is the code for that. So this part, initially a producer will produce its resource, and then it waits on empty. This means that if the empty is 0, that means the buffers are full, right? Empty count is 0 means the buffers are full. Then you cannot add more into it. Therefore, you have to wait until buffer becomes empty. Empty as in not whole thing empty. One buffer, you have to wait for one buffer to become empty. So it waits here. If suppose the number initially empty was initialized to n, right? So then it's not 0. So then it can move on to this. wait mutex. So this is to ensure that now we are going to move on to the critical section. So therefore, we have to prevent context switches, not prevent context switches, but we have to prevent any other process from modifying the critical section. So then at this point, mutex was initialized to 1. That means if you are waiting on mutex, as I mentioned before, wait is used to decrease the value. So 1 becomes 0. So at this point, if a context switch happens, any other process will be forever waiting on mutex, because as I mentioned, we are not allowing it to go to the negative side. So since it is 0, it will keep on waiting. After performing the necessary modification to the critical section, we will signal the mutex. Signal is used to increment the value. So mutex goes from 0 to 1 here. Then you see that now any other process can execute its critical section. And then we are signaling full. So we are increasing the full count as well. So this is the structure of the producer process. When we consider the consumer process, it's also similar. Initially, although it waits on full. So you see, if the full count is 0, that means there are no resources in the buffers. All the buffers are empty, which means a consumer technically cannot proceed because it needs to consume resources. So therefore, it waits until at least one full buffer is there. So it waits on full. And now assume that this actually executed before the consumer process. So now we know that full isn't 0, it's actually 1. So, okay. Then it moves on to the next part. So it waits on mutex, which means again, we are entering the critical section. So it consumes a resource and does the necessary modifications, and then it signals mutex so that it gives the a go for the other processes to enter the critical section. And then it signals empty because now we have to increase the empty count. Okay, so that is basically the solution for the bounded buffer problem using the semaphores, mutex, full, and empty. The other problem is the readers writers problem. So it's a little bit different because even though we have, as before, two kinds of processes here, readers and writers, we can allow multiple readers to read the critical section because they are not going to perform any modifications. We don't care if two readers, any number of readers, read the critical section at the same time. But when it comes to writer processes, we cannot allow them when someone is reading, or we cannot allow two writers to write at the same time, so that it creates some kind of synchronization issues. So that is the difference between this and the previous one. So here we are using a different set of semaphores, which is the first one is the read write mutex, and the second one is mutex. Third one is read count, which is just a integer. So both of these are initialized to 1, which means that it's not locked initially, and the reader count is 0. So let's look at the structure of a writer process. So this initially waits on read write mutex. That means when a writer process is entering its critical section, then we cannot allow another writer or another reader to enter into the critical section. Why? Because there are some modifications happening. So after performing its writing, then we can signal mutex, so it gives the go for the other processes. So this is quite simple. When we consider the reader process, it's kind of complex, but not so much. So the first thing it does is it uses the mutex semaphore to perform some updates on this part. So it waits on mutex first and then increases the read count because it's a reader process. It increases the read count. So initially it was 0 and now it will be 1. If the read count is equal to 1, then what it does is it waits on read write mutex. What does this mean? So we have to wait until if there's any writer writing at that time, we have to wait until it has finished its writing. Because when a writer process is inside its critical section, we cannot allow a reader to enter into the critical section. So it waits on this mutex. So suppose there are no writers writing at this time, then it can proceed. It can proceed. So the next thing it does is it signals the mutex, which means now any other reader process can actually read. Not the writers, because they will have to wait for this. But any other reader process, they will have the same structure. It will wait on mutex. But since we increase the mutex here, it can proceed as well. So this allows multiple readers to read at the same time. So when the reading is performed, it again waits on mutex because it's going to do some modifications. It decreases the read count because now it's done reading. And if the read count is 0 only, we signal the read write mutex. That means if this is the last reader only, we allow a writer to write into the critical section. Else, we move past this. We don't execute this because even if there's one reader process still reading, we cannot allow a writer to write. So then after signaling the mutex, this is completed. Yeah, that was the readers writers problem. Next we have the dining philosophers problem, which is kind of a different problem. Basically, this is the graphical representation. So assume there are 5 philosophers and they are dining and they need chopsticks. So however, there aren't any even number of chopsticks. There's only 5 chopsticks. So you need both to eat. So therefore, all 5 cannot eat at the same time. So this is how a philosopher eats. Again, these are all metaphors. So it waits on the chopstick on its left side and then right side. And then if both are available, it can eat. Otherwise, it can eat. And after that, it can release the chopsticks and then think. Yeah. So this algorithm or like this process, the problem with this process is that there can be a deadlock. So we'll come to deadlocks later. So basically a deadlock means like none of the processes can actually complete. So suppose let's use this diagram. Suppose every one of these philosophers picked up the chopstick to their right. And this one will pick this and so on and so on. Then all of them will have one chopstick at hand, but none of them can eat. Therefore, none of them can think. So it's kind of stuck there. So that kind of situation is called a deadlock. So to handle this, we have something called a monitor, which is kind of a language abstraction. It's declared as a class. So you can go through this code. Basically, this is the structure of the solution. Dining philosophers dot pickup and then eat, then dining philosophers dot put down. So what this means is that so let's consider the process pi. So we change the state to hungry and then we test I. So this test method, this one, this changes the state of PI to eating only if the left side philosopher and the right side philosopher is not eating, and also if the philosopher in question is hungry as well. Otherwise it is kept on thinking. So this test I is used to check both sides first, and then only it will change the state to eating. And after that, so assume that a context switch happens in the middle. So then PJ executes. So then PJ state of J is set to hungry. And then if you test J, J will not be able to eat if J is next to I, because I is already eating. So this is how that handling of critical section is implemented using this. So when a philosopher is actually done eating, it can actually change the state to thinking, and then what we do is we test its neighbors, right side and left side philosophers. Yeah, so those are the classical problems with respect to critical section problems. Yeah. So in this case, there's no deadlock, but starvation is possible. Starvation actually means, I didn't mention before, starvation means if a process keeps on like එයා කන්නෙත් නැහැ අනිත් අයට කන්න දෙන්නෙත් නැහැ වගේ. Like it's not interested in executing its critical section, as well as it holds on to the resources so that the other processes also cannot execute their critical sections. So that is called starvation. Yeah. Any questions? Just let me know. Moving on to deadlocks. Deadlocks are actually, yeah. So this is like a situation where there must be n number of variables, sorry, n number of processes sharing resources, so that they are like preventing each other from completing, so that all the processes are kind of stuck in a situation like that dining philosopher problem, where every one of them holds a chopstick and none of them can eat and none of them can think, so they're stuck. So for this, there are a set of resources and a set of processes, and basically the idea here is that all of the processes will need some resources, but they aren't available because some other process is holding on to it. So there are these 4 conditions that must occur simultaneously for a deadlock to happen. So this, let's go through them. First is mutual exclusion, which means only one process can use a resource at once. And the other one is hold and wait, which means a process holding at least one resource is waiting for resources held by other processes. The other one is no preemption, which means a resource can be released only by the process holding it. And the other thing is circular wait, which means that something like this: P0 waits for P1, P1 waits for P2, and so on, and then Pn waits for P0 to finish. So it's kind of like a circle. So there are some things, some methods that we can use to handle deadlocks, which are deadlock prevention, deadlock avoidance, recover from deadlock, and then we can basically ignore. The last one is actually not a solution, but anyway. So prevention, when we consider prevention, we can actually address the previous 4 points that we saw for a deadlock to happen. We can actually, considering mutual exclusion, we can, like this is not needed for read-only files, so we can omit that for read-only resources. That means shareable resources. However, we must have them for non-shareable resources such as printers. And hold and wait, we can restrict the processes so that processes must request all the resources at once, so they don't actually wait. So if like a process can request resources at the time it is needed, but here we are saying that no, you must request all the resources at once, so that you can avoid waiting. Considering no preemption, we can restrict processes so that if PI is holding some resources and requests another resource and that resource is not available, then all the resources it is currently holding are released to the system. And then circular wait, we can implement a mechanism such that we can number the resources and then restrict the processes to request only in strictly increasing order. So this is kind of difficult because it's like we have to determine like what is the ordering of resources, etc. So that is the deadlock prevention. When we consider the other thing, which was deadlock avoidance, we can avoidance means we can prevent deadlocks from ever happening by preventing these conditions. So some algorithms require like the maximum number of resources a process may use in advance so that it can identify a safe state. So what's a safe state? It is like a sequence of processes that would not result in a deadlock state. So we have this set of processes P0 to Pn, and we are trying to identify what would be the correct sequence so that it does not result in a deadlock. So to identify deadlocks, we have a graphical kind of solution, which is the resource allocation graph. Basically, we are representing a process here by a circle and then a resource by a square. So a resource can have many instances. So for example, printer. So if you have 4 printers, then there are 4 instances here. And then this is PI requesting an instance of RJ. So the arrow goes from PI to RJ. And if PI is occupying an instance of RJ, then the arrow goes to the other side. So this is an example of a resource allocation graph. P3 is holding R3, however, P2 needs R3. P2 is holding R1 and an instance of R2. However, P1 needs R1 and is holding an instance of R2 as well, and no one is using R4. So when you look at this graph, you may assume that, okay, so if there are cycles here, then we can easily say there's a deadlock. Correct to some extent. However, so this is a graph with a deadlock. So you see P3 needs R2 to finish, and since it's not available, it cannot finish. P2 needs R3 to finish, but R3 is occupied by P3. Since P3 cannot finish, P2 cannot finish. And then when we consider P1, it needs R1, but however, R1 is already occupied by P2. Since P2 cannot finish, P1 also cannot finish, then all three processes are stuck here forever. So this is a graph with a deadlock. So when we consider like cycles are important for resources with single instances. So if there are single instance resources, if you consider a graph with a cycle, then you can definitely say, okay, there's a deadlock. But in case of situations like this, where there are multiple instances, you cannot directly tell by the graph, because this is a graph with a cycle but no deadlock. So if you go through this, you can identify that it has no deadlock, even though there's a cycle here. So if a graph contains no cycles, then we can say no deadlock. However, if a graph contains a cycle, then if there's only one instance per resource, then yes, there's a deadlock. If there are multiple instances, then there's only a possibility of a deadlock. We cannot say for sure. So for this, we need some advanced algorithms to identify like in case of multiple resource instances. So one such thing is the Banker's algorithm. So this is, as I mentioned, like one of the algorithms which requires the maximum number of resources a process may need to identify a safe state. So it uses all these data structures: available, max, allocation, and need. Basically, what you have to do is like this is like the initial setup. So these are all the allocated ones. So P0 already has one instance of B, and it actually needs a maximum of 5, which means it needs 4 more to complete. And there are other resources as well. So if all of the resources are complete, only it can finish. So you see, when you are given something like this, and we have an available list as well. So these are the available number. So you have to calculate the need matrix. Need means max minus allocation. What is the maximum it needs and what is currently allocated. So how much does it need more? So according to the need, you have to find something which is a process which can actually accommodate the available resources. So we have 332 for A, B, and C. So that means we cannot execute P0 at first because it needs 7 instances of A. So since we have 332, we can execute P1 or this. Yeah, only those two. Sorry, P1 and P3. So you can choose something like this. So you can go through this sequence. This is a safe state because it doesn't actually provide deadlocks. So it's kind of a simple algorithm. However, you have to have an idea on how these matrices work. So that is about deadlocks. So basically, regarding the other 2 points, not the 2 points actually, the recovery from deadlock. Basically, you can either terminate a process or take a manual action or resource preemption. Basically, we can choose a process and release all its resources. So there are techniques like that. Yeah, so that's it about the deadlocks. Is there any question you can ask? Then I'll be moving on to the CPU scheduling. So when we consider CPU scheduling, there's something called CPU burst and IO burst. So processes can be divided into CPU bound processes or IO bound processes. It means that CPU bound processes have long computations, while IO bound processes have like they are mostly waiting for IO devices. So during the CPU burst, it needs the CPU, and during the IO burst, it doesn't. So we are trying to, since we have like limited CPU resources available, we are trying to, through CPU scheduling, we are trying to find like what is the most efficient sequence of processes to utilize our CPU. So there's something called preemptive scheduling and non-preemptive scheduling. Basically, if you consider that state of processes which I showed earlier, was this? Yeah. So scheduling can happen either when it's suspended or terminated, or it can happen at any time. So scheduling that happens only at suspension or termination, it is called non-preemptive scheduling, while if a scheduling can if a scheduling can happen at any time, it's called preemptive scheduling. Yeah, so we have some criteria for that as well. We take the slides here. Yeah, so these are the criteria. We have these attributes which are like used to compare scheduling algorithms. So these are our goals. We are trying to maximize CPU utilization, throughput, turnaround time, waiting time, and response time. So there are a list of scheduling algorithms. The first thing is the first come first served scheduling. So this is actually very simple. Basically, it's a queue. So we execute in whatever order the processes come. So if P1 comes, it is executed, and we have the burst time. So you may have to draw Gantt chart like this. So you start from 0, and then burst time is however long you use the CPU. And after that, since P2 uses only 3 milliseconds or microseconds, it goes from here to here, and then you can actually find the flow. So this has actually this one, convoy effect, which is and like suppose all the suppose these are like IO bound processes, P2 and P3. So then if a CPU bound process is occupying the CPU for a long time, then a number of IO bound processes get backed up behind it, something like this. So it's kind of not efficient. So in this case, P2 and P3 can quickly finish their task and move on to their IO burst cycle, so that P1 can then occupy the CPU. So this is called the convoy effect, which is seen in first come first served scheduling. The next one is shortest job first, which is basically we are looking at the burst time. So this something like this is actually easy. So if the next burst time is given, we can directly draw the Gantt chart. However, SJF is actually looking at the next burst cycle. So it has to do some predictions on what would be the next, the time period of the next burst cycle. So to do that, you can actually, you have several options. first the user can set limits for each job. So the CPU burst is actually manually set by the user, or you can analyze runtime characteristics and then statically measure the burst time, or you can take the exponential average, which is like predicting the next burst. So this is the equation used for that. So here, this tau n plus 1 is actually the estimated value of the next CPU burst, and this Tn, this one, should be n plus 1, and then Tn, it is actually it is the actual value of the current burst, and we have alpha. Alpha is a weighing factor for the relative importance of recent data versus past history. So this is the past history, the second term, this one minus alpha, a whole thing multiplied by tau n. So this is the past history, and recent data is the alpha multiplied by Tn. So suppose alpha is equal to 1. That means the second term will be 0. So the past history is ignored, and we assume the next burst, tau n plus 1, will be equal to Tn, because alpha is 1. So then next burst is equal to current burst. If alpha is 0, then the first term becomes 0. So then we don't consider the recent data or all measured data. We just assume a constant time. So the next burst cycle is actually equal to the previous burst cycle. So alpha is usually taken as half, which means we are giving equal importance for the two terms. So yeah, that is the SJF, and yeah, there's some examples. So the other thing is priority scheduling. Priority scheduling is basically you are giving a number like a priority for each process. This is actually very simple. So you choose the one which has the highest priority, and then you can calculate the average time as well. So here in case P2 is number 1, so P2 comes first, and then the second priority is P5. So you execute P5, and then P1, P3, and P4. So it's quite simple. And round robin, this is also basically this is actually very similar to first in first out, but here there's a time quantum. So there's a constant time that we are allowing a process to occupy the CPU. So that value is called Q. So let's look at an example. So Q is equal to 4, which means P1 is P1 has arrived first, so we are taking P1, but we are only keeping P1 for 4 milliseconds or microseconds. So after that, we preempt that and then take P2, something like that. So in this case, we have to consider the size of Q. In this case, that is 4. However, when we consider the size of this time quantum, if it is too large, that means it reduces into first in, first out. Basically, whatever comes first is executed, and then the others. So in this case, time quantum is 12. So then it basically becomes a first in, first out scheduling algorithm. If the time quantum is very small, that means, for example, 1. So each 1 millisecond, the process is preempted and another one is run. So there's like, when we consider the context switches here, if the time quantum is very large, we have 0 context switches. But if the time quantum is very small, then we have a large number of context switches. So context switches are very expensive, so that is not very efficient as well. So we have to actually consider what would be the most optimum time quantum here. And then we have the multi-level queue. This is where we maintain two queues. So in the previous ones, we had only one queue for the processes. Here we consider two queues, one for interactive processes and one for batch processes. And we have separate scheduling algorithms for each queue. However, the processes cannot jump to any other queue. So the queues have priority levels. Yeah. The other ones, we have other scheduling algorithms as well. The other one is multi-level feedback queue. So this is similar to the multi-level queue that we discussed earlier. However, here we can, the processes can move between queues. Why is this implemented? Because to implement aging. So aging is a technique that we use to prevent starvation. So when time goes on, we increase the priority of a process so that at one point we are ensuring that it would get executed. That is called aging. So processes are moved from one queue to another in this multi-level feedback queue. And then comes thread scheduling. This is a very theoretical part. So we have user level threads and kernel level threads. So here we are not considering scheduling processes. We are scheduling threads. So you can read about that. There's like multi-threading models as well. Yeah. So next comes multiprocessor scheduling. So in case of multiprocessors, we have to utilize all the CPUs in an effective manner. So when we consider multiprocessor systems, there can be like heterogeneous or homogeneous. Heterogeneous means different kinds of CPUs, while homogeneous means the same kind of CPU. So there are two approaches here. The first thing is asymmetric multiprocessing. So in here, one processor is the master, acts like the master and controls all activities and runs the kernel code, while the other processors runs the user code. So critical system data isn't shared among processors. The symmetric multiprocessing is actually where each processor, like there's no master here. So each processor schedules its own jobs, and this is currently the most common. There's a common ready queue for all the processes, and a common ready queue for all the processors as well. And there's something called processor affinity, which means like an attribute associated with each process to maintain on which processor that process is executing on. So this is actually important in case of cache memory. You know that the CPU actually maintains cache memory for quick memory access. So if we are like changing CPUs constantly, we can't use that cache memory. So it becomes ineffective. So we are always trying to like put the same process to the same processor. So there are two types of affinity, soft affinity, which means like the system tries to keep the processes on the same processor, but like there's no guarantee. Hard affinity means the same process is scheduled to the same processor. And here we also have to consider the load balancing, because one processor cannot be overloaded while the others are kept idle. So we have this mechanisms called push migration, which is like a separate process which is run periodically. It moves processes from heavily loaded processes to idle ones. Pull migration means the other way, where idle processors pulls jobs from the overloaded processors. And then the other one is we have real-time CPU scheduling. So this is actually used for time critical applications. So basically there's two types of real-time systems. Soft real-time systems are where even if you didn't meet the timing constraints for a job to finish, you will have performance degradation, however no critical failures. However, in case of hard real-time systems, the task must be serviced by its deadline. So if you fail to do that, there will be a total system failure. So in this case, there's like two types of latencies that affect the performance. One is called interrupt latency and the other one is called dispatch latency. When you consider interrupt latency, this is the time taken from the arrival of an interrupt to the start of the interrupt service routine. We learned interrupts earlier. So when an interrupt comes, from that point onwards to the start of the interrupt service routine, the time taken is known as the interrupt latency. And we have these things called interrupt processing here, which means like determining which interrupt has occurred and which interrupt handler to run. And then we have the context switching involved as well to remove the currently running process from the CPU and then saving its state and then loading the interrupt service routine. So those things come under interrupt latency. And we have the dispatch latency, which means basically the context switching part, time taken to take the current process out of the CPU and then switch to another. In this diagram, there's the conflict phase, which means like preempting, like taking the process off the CPU and then releasing its resources, whatever the resources it holds. And then dispatch means choosing another process to run on the CPU. The last thing is the priority-based scheduling. So here we consider periodic ones for real-time systems. There are some attributes here like the constant time required to execute. So this will be the CPU burst, which is denoted by T, and a deadline by which the task must be completed. And then we have a period P. So two examples for this is the rate monotonic scheduling, where we take the priority of a process as inverse of its period. So you see the shorter periods have higher priority, longer periods have lower priority. So in this case, P1 is assigned a higher priority because its period is 50, while P2 has a period of 100. Yeah. So the other example is the earliest deadline first scheduling. So in this case, consider this like in the rate monotonic scheduling, like if the deadline of P1 is 50 and the deadline of P2 is 80. So in this case, when P1 is executing, since P1 has a higher priority, P1 is executing first because its deadline is arriving first. So at 50. Then after that, from this point, the deadline which arrives first for the next cycle is 80. So then we let P2 finish. We don't preempt P2 as in the rate monotonic scheduling, because if not, we cannot finish P2 by 80 in this case. So we let P2 finish, and then we again take whatever is coming, whatever processes deadline is coming first. So here we consider the deadline, and whichever is the earliest, we give the priority to that first. So that is the summary of all the CPU scheduling algorithms. So basically, you just have to look over the Gantt chart and how to schedule the processes and identify their priorities in such a case. And also, you may have to calculate the average waiting times, etc., by considering their arrival times and so on. Okay. So the last part, I guess, would be the page replacement algorithms. So I'll clear this. So when we consider memory, there's something called virtual memory. So virtual memory, so memory is actually divided into something called pages by the OS. This done by the OS, and this pages are swept in and out of the memory, and we can store it in the disk. So there's a separate space for these pages to be stored in the disk. So pages are basically like segments of memory, and this paging mechanism, or the virtual memory, actually gives an illusion to the processes, like they have more memory than they actually have. So we only like take the pages of a memory into the RAM when a process needs it. So pages are actually swapped in and out. So suppose we have a page P1 and P2. So these are not processes, these are pages. So when suppose there's something called P5 as well, we initially stored in the hard disk. So in this case, our memory is already completely occupied. So in this case, when we need this page, we actually take something out. For example, this is just an example, and then we can take P5 here. So this gives the process that it has more memory than it is actually available in the real scenario. So this is what virtual memory means. So demand paging is actually the process where these pages are swept in only when the process needs them. So on demand. So in this case, like when a process actually requests a page which is currently not available within the memory, it is called a page fault. So in this case, P5 was not available and the process requested it, so we had to bring it from the disk. So page faults are actually expensive because we have to, there are several steps we have in like handling a page fault. So the number one is locating a free frame. So we have to have a free slot to bring the page from the disk. And then we have to perform a disk operation to bring the page from the disk to the memory. And the third step is when this IO operation is completed, we have to update the page table. So page table is something that we maintain to check whether to check what are the pages currently available and what are the pages not. And the fourth step is restart the instruction, which caused the page fault from the beginning. These are the 4 steps available when we are considering a page fault. However, in situations like this, when it required the P5 page, we didn't have any available slot. So now we have to do something. We have to replace something here, P1, P2, P3, or P4. Take it out, and then we have to put P5 into our memory. So choosing which page to replace is basically the what's happening in page replacement algorithms. So that is the context. So let's look at the algorithms. Let me share the screen. Okay, so the first algorithm that we have is first in, first out. Here, basically, you will be given a string like this. So these are the sequence of requests by the process. So first it requires the 7th page and the 0th page and the first page and so on. So for each of these problems, you have to like draw something like this. So first you require the 7th page. So initially, since assume that we don't have any pages available in memory, so that's a page fault. So we have to bring the page from disk to memory. So this is the initial case where we have a free slot. So we bring the 7th page here, same for 0, same for 1. Now when 2 comes, we don't have any free slot available. Therefore, we have to figure out what to replace. So in, first out, this is basically a queue. We take out the page that came first. In our case, in this case, that was 7. So we take 7 out, put 2 in. And when we consider 0, it is already available. So we don't have to bring it. And then we consider 3, it's not available. So we have to take something out. So the one that came first from 2, 0 and 1 is 0. So we take 0 out and put 3 into our memory. So it goes on like that, and you can actually count the page faults as well. So there are 15 page faults happening here. There's something called Belladis anomaly that is happening in first in, first out page replacement algorithm. It means that when you increase the number of free frames, you might assume initially that the number of page faults may decrease. However, it is not the case. Sometimes it may also increase. So in case of first in, first out, when the number of frames were 3, it initially recorded 9 page faults. However, when you increase the number of free frames, it displayed 10 page faults. So this is called Belladis anomaly. So this is usually seen in this algorithm first in, first out. So adding more frames don't always cause less page faults. Something to remember. So then we have the optimal algorithm. This is actually really hard to implement. It's more of a theoretical solution because we are trying to replace the page that will not be used for the longest period of time. So theoretically, it is possible. We can see that this is the reference string. And when we are replacing a page at this point, The one that will not be used for the longest time is 7. 7 is only requested at this point. So we are replacing 7 and so on. So this will actually result in the least number of page faults. However, this is very hard to implement because we have to do some predictions here. Uh, so we have the least recently used algorithm next. So this uses the past knowledge rather than the future. So when compared with the first in, first out, uh, FIFO actually looks at the oldest load time. However, LRU looks at the oldest use time. So least recently used means 701 at this point. What was the thing that we used least recently, not the most recently? So least recently used is 7, then we replace 7. So then 0 again when it comes to 3, the least recently used was 1. So if you look at the string, you can identify what was the least recently used. It's always on the leftmost side. So we keep on replacing at that point, at that way. So there's like two kinds of implementations you can use here, which is the counter implementation. So here I'll go back to the whiteboard. So this is something like this. Counter implementation is we have pages 1, 2, 3, and 4, and let's say 5. And we have this page sequence, let's assume. So when assume that we only have 4 free frames, then when it requires 1, what we do is we copy the current clock value. So let's assume it's 1, then it requires 2, then we copy that 2, this is again 3, and when it comes to 5, then the clock value is 4. Okay, so we already have 4 frames in memory. So when it again goes back to 2, then we are trying to access something which is already in our memory. So what we are doing is we are updating the counter value to the current clock value. So it's 5. Then when it comes to this place, which is the 4, we have to replace something. So we have to replace the one with the entry with the smallest counter value. So in this case, that is 1. So we are replacing 1 with 4. So in this case, the counter value is 6, and so on. This is the counter implementation. So the stack implementation is actually very similar. So the simple. So you are maintaining a stack 1, 2, 3, and 4. Sorry, 5. And the idea here is that whichever the most recently used page is always taken to the top of the stack. So in case of a page replacement, you are actually taking the thing out from here, from the bottom of the stack. So in the case of this place, when it tries to access 2, we have to erase 2 from here and then add 2 to the top of the stack. I'll just put it here. And then when it accesses 4, then we have, since this is already full, we have to take the one in the bottommost page. So that is 1. We take it out and then put 4 to the top of the stack. So this is the stack implementation. Yeah. So let's go back to the slides. Yeah, okay. So there's something called second chance algorithm. This is also similar to the recently used algorithm. So what it does here is, this is basically a first in, first out. However, there's a reference bit provided by the hardware to give a second chance for a page to stay in memory. The logic here is that there's this pointer, next victim pointer, and this is kind of a circular queue. The pages are like a circular queue. So this next victim pointer keeps on advancing, checking the pages one by one until it finds a page with reference bit 0. When it finds a page with reference bit 1, then when it advances, it sets the reference bit to 0. That means I'm giving you another chance to stay in the queue. And when it finds a page with reference bit 0, then you can take it out. So that is the second chance algorithm, also known as clock page replacement algorithm. So if all the bits are set, that means all the reference bits are number 1, this actually reduces into the first in, first out algorithm. And lastly, we have the enhanced second chance algorithm, where we actually use another bit which is called modified bit. So assume I don't have a graphical representation for that. So assume there's another column here next to the reference bit. It is called modified bit, and it also has ones and zeros. So in this case, we have 4 cases. So a page can have 0, 0, 0, 1, 1, 0, or 1, 1. So 0, 0 means neither recently used and not modified. So the modified bit is set if we have modified the page that is in memory, which is like there's a difference between the page in the memory and the page in the disk. Like I told you, okay, I erased that. Like when it goes to the disk, like we are taking pages from disk to the memory, right? So if the page at this point, let's say P5 and P5 this point is actually modified. Now this page is modified after taking it back to the memory. So therefore, in this case, modified bit is set to 1. So when we talk about modified pages, we can't completely discard it. We can't just take it out and throw it away. We have to actually save the modified pages again back to the disk. Otherwise, we will lose the modification. So that is the idea here, why we use a modified bit. So so this is neither recently used, neither recently modified. So we don't have to actually write it back to the disk. We can just take it out and discard it. So this is the ideal page to replace. So if you in the circular queue, if this pointer finds 0, 0 with next to a page, then that is the ideal victim. If this is 0, 1, that means not recently used, but modified. So it's not quite as good, but we have to write it out to the disk before replacing it. 1, 0 means recently used, but clean. However, since it is recently used, it may be used again. 1, 1 is actually the worst page to replace because it was recently used and also it was modified. So it will probably be used again. And if you are replacing it, you will also need to write it out, write out the replacement. Yeah, so difference between this algorithm and the normal, like the default second chance clock algorithm is that in this enhanced second chance algorithm, we are trying to give preference to the pages that have been modified in order to reduce the number of disk operations that we are going to do. Yeah, so those are all the things that I plan to discuss today. Let me know if you have any questions. Any questions in any language, you can send in chat as well.
Anyone of you have any questions? You can raise in English or Sinhala. I hope that there are no any more questions. So let's wind the session then. Yeah. With that, we are officially concluding our final session on operating systems for today. So this marks the end of the bootcamp series organized by the Computer Science Society of the University of Colombo, with 4 continuous days of subjects for first year CS and IS students as an exam guide for the upcoming semester exams. We hope that the sessions were fruitful and helpful for acing your exams. And we thank all the participants of our 4 sessions for their cooperation and active involvement. A big thanks goes to the speakers, Dalana Dharmatilaka, Isuru Harishchandra, Harsha Bevikrama, Kesara Karanaguda, and Ilma for their valuable time and effort to make the sessions very interesting and interactive. Thank you very much once again. So now we are signing off for the day, and let's meet in the future events with more exciting and interesting sessions of ComSA.